Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be talking more about isomers. So firstly we're going to define what we mean by isomers. We're going to look at the different types of isomers that exist because we categorize them in particular ways, and then I'm going to show you some examples of each of these types of isomers. So firstly, let's have a look at these six structures for compounds. We can see here that we've got various different kind of connections of black carbon atoms, white hydrogen, red oxygen, and green chlorine atoms. But that depending on exactly what combination that we have, that they're connected up in different ways. These six compounds represent what we call isomers. They have the same molecular formula, so that is they've all got the same number of different atoms, 6 carbons, 3 hydrogens, 3 chlorines, 1 oxygen, but they're connected in different ways, which gives rise to different structural formulae. So that when we draw them out, when we look at them visually, that we can see that they are different compounds. Depending on where the chlorines are relative to each other, relative to the rest of the molecule, they're put together very differently. So we call these 6 compounds isomers, okay, for same and then piece, essentially. So there's 3 main types of isomers that we encounter in organic chemistry. The first one is called chain isomers. We have position isomers and functional group isomers. So depending on how the relationship between these different connected versions will dictate what type of isomer we're talking about. And it's important that we can understand which type we're talking about because there'll be differences in their relative properties compared with one another. So chain isomers, we can see here these 2 particular compounds are called chain isomers. We know that hydrocarbons tend to exist in these chains of carbon atoms with hydrogens attached. But we can see that we can take the same combinations of carbon and hydrogens and connect them in a different way so that we have branches at different points. So here we're talking about chain isomers being structures that can either be straight chain, like the one on the left, or branched, like the one on the right, in being these different types of substances. So this one here we have on the left, pentane, because we have a 5-carbon chain, whereas this one is called 2-methylbutane because we have a methyl or a 1-carbon group at position number 2 of a 4-carbon chain. So these 2 compounds will have different physical properties based on the differences in their dispersion forces because of the shapes of the molecules. So these are chain isomers. Now we come to think about position isomers. So position isomers, as the name might lead you to expect, the differences in the position of certain types of atoms in the structure. So we have the same atoms, but these particular functional groups or particular atoms are connected in a new position on the carbon chain, but they don't change the functional group of that compound. So here, if we look at this, we've got 2 chlorine atoms. We're connected to carbon number 1, or connected 1 to carbon 1 and 1 to carbon 2. So the chlorine is in a different position. Okay, so they give rise to different locants because we use a number to refer to each position of each chlorine atom. So we have 1, 1 to show they're both on this one, and then 1, 2, dichloroethane. So positional isomers, where we've the same atoms, we're connected into a different spot on the chain, different locants, meaning a fundamentally different name. But one thing that I do want to encourage you to be careful about is that if we look at each of these 6 structures here, you think, whoa, there's a whole massive collection of isomers for this one compound. But the reality is, and now I want you to be careful, these are all the same compound. That is, if you made a model of this with a modeling kit and held it in your hands, you could make it look like any one of these representations without breaking or reforming any bonds. Position isomers exist where you have to physically, if you made a model, you have to detach some atoms and connect them to a new spot. Whereas the reason that we end up with these images comes down to the difference between 2D versus 3D representation. We're trying to represent a 3D molecule in a 2D way, but the reality is that this bond in the middle here can rotate. If you made a model of it, it's able to actually spin around like this without breaking. And so then depending on which perspective you're looking at it, you will see it look slightly different. Okay, so it's just one of those things you have to be careful, have to be a bit cautious and think about what it's trying to represent in 3D. Do they connect up to fundamentally different carbon atoms, to be able to decide if they're position isomers or not. And lastly, we come to functional group isomers, where we've got the same atoms, but they're connected in such a radically different way that we end up with different functional groups. That is, the compounds belong to totally different families altogether. So for example, we look at these two, pentanal and pentanone, or pentantuone to be more specific, I apologise. So the position of this oxygen atom, or this carbon double bond oxygen, carbonyl kind of group, dictates whether it's an aldehyde, like this one on the left, or a ketone, or an alkanone, the one here on the right. Likewise, we have these two, where we've got the oxygen, the position of the oxygen, is it between two carbons, or is it between a carbon and a hydrogen? That then dictates that we're belonging to totally different hydrocarbon families. Still have the same molecular formula, the same number of atoms, but the difference in their connection means different functional groups. And the reason that that's particularly important is that that gives rise to massively different physical properties and chemical properties between the two compounds. You know, aldehydes and ketones have a lot of similarities in many properties, but their chemical reactions are quite different. Or there's certain ones that aldehydes can do that ketones can't, for example. Okay, and so that's something that we need to be mindful of. So we have an aldehyde versus a ketone. This is a type of compound which is beyond our syllabus, but it's called an ether, and this is called an alcohol. So the difference in those connections gives rise to different functional groups and therefore different physical and chemical properties. So we looked at what are isomers. We've got compounds with the same molecular formula, but the atoms connected in a different way, giving rise to different structural formulae. We have three main types of isomers: chain, position, and functional group isomers. We classify them based on different characteristics, and they give rise to different types of relationships. And we had a look at some examples of each one. All right, thanks very much for watching. Don't forget to like and subscribe. Bye for now.